how do multiple charges interact with each other? More than two. Before we took a look at how we have a pair of charges, just like a positive and a negative charge, or a negative and a negative, and we said, okay, they either attract or repel, and we have Coulomb's law to describe the amount of force each of them feel due to each other. But what if we had three charges? Or what if we had more? So the problem is not as hard as it seems. It still involves using Coulomb's law. So let's take a look at another example of finding forces between charges. Multiple electric forces on point charges. Two charged particles with charges of positive 7 microcoulombs. Remember, that's the Greek letter mu, and it's a prefix meaning micro. And we have a negative 14 microcoulomb charge. They're held in place and separated by a distance of 10 millimeters. What is the net or total electric force acting on an electron, which is placed between the two fixed charges, which are listed above, 7 and 14? It's placed 4 millimeters away from the positive charge. So you can kind of see here in the diagram that's sketched out that we have fixed charges on the end. We have the positive 7 and we have the negative 14 microcoulombs. But now there's an electron here in the middle, which is placed somewhere between the two, but we specifically say that it's 4 centimeters away from the positive charge. So it's closer to the positive charge than it is to the negative charge because the total distance is 10. So the remaining distance here to here is 6. So let's quickly sketch this out. So we have that along this axis. Let's make a habit of calling some direction positive. In this case, positive x. Let's say that's to the right. And we have our charges. So we have our positive on the left, fixed. I'm going to call this one Q1 in the problem. We have another fixed charge on the right, negative, and that's Q2, let's call it. So we have those two charges. We know the values were given. Q1 equals positive 7 microcoulombs. We know Q2 was negative 14 microcoulombs, so it's twice as much charge in this case. And we have a third charge, which we know is an electron. So the charge is not flat out stated, but it's implied that we should know it because it's an electron. Electrons have the charge of the elementary charge or the electron charge constant, which is 1.6 times 10 to the minus 19th coulombs. So technically, if we call this Q3 for our electron, we know that Q3 has a value of negative 1.6 times 10 to the minus 19th coulombs. Okay. These are in microcoulombs. This is given already in coulombs. Now, the question was to find the net or the total force acting on this electron in the middle of the two due to the other charges. So how do we find the net or total force? So net or total implies to consider all the forces acting on it. So what we're going to do is let's count up the number of forces that are acting on it and what direction they point. So what we do is we consider that every single charge pair, every single pair of two charges will experience attraction or repulsion and follow Coulomb's law. Coulomb's law will work for two charges at a time. So what we're going to do is we're going to say, okay, if we have to involve the electron because we want to know what the force is on it, then let's talk about, let's say, the charge on the left, and we cover up the charge on the right and just pretend it doesn't exist for the time being. These two charges are unlike or opposite charges, so they attract towards each other. So specifically, I'm only going to talk about the force on the electron because that's what my focus of the problem is to find the forces on the electron in the middle. So I'm only going to draw the force on this one. So we know that because it's attractive towards this Q1, there's going to be force on Q3 toward Q1 along this line. My notation is going to be that it's going to be the force on 3, so I write 3, caused by 1, so I write 1. Sometimes people flip these around, 3, 1, and 1, 3, and they write them differently, but in the end it doesn't matter as long as you know what it means to you and to the person who's reading it. So in my case, I'm going to say that the first number represents the particle that I'm talking about the force on, and the second number is referencing to what it's caused by. So force on 3 caused by 1. So that's due to the charge on the left. But now if I instead cover up the charge on the left, I can talk about the force caused by the charge on the right. So we know that between these two only, we know that they're the same kind of charge or they're like charges, so they repel from each other. So what that means for this charge is it wants to get away from this charge, so it's going to feel force away from it to the left. So this is completely separate from the other force that we drew in. Call this force F3, so it's the force on 3 caused by 2. Okay. So F31 and F32 have nothing to do with each other, they're independent. But F31 points to the left because it attracts to the positive, and F32 points to the left because it repels from the negative charge. So that tells us the directions. We're going to take care of the directions later. Now we have that, let's figure out what the value of F31 is and what the value of F32 is. So we can use Coulomb's law to calculate these. So for instance, F31 described by Coulomb's law is just K Q3 Q1 over, let's call this distance R31 squared. So being very specific about everything, because we're talking about charges 3 and 1, we'll use Q3 and Q1, and we're going to call distance R31 to indicate that it's the distance between 3 and 1. Okay. Don't forget to square it. So we should have all these. We already know what the distance between here and here is. We know that this distance, R31, we know R31 is given in the problem as 4 millimeters. Okay. Now we know that the total distance between the two is 10, so the remaining distance, which we'll later use as R32, has to be the remaining 6 millimeters. Okay. So at this point we just plug it in and calculate it. So we have that K is 8.99, 10 to the 9th Newton meters squared per Coulomb squared. Plug in the magnitudes of each of these. Remember absolute value because we only want how big the force is, not the direction. So ignore all minuses. So Q3 is 1.6 times 10 to the minus 19th coulombs. And we have Q1 is 7 microcoulombs. Now, you could go through the whole process of, set up your conversion and then work out the conversion, but we already know that a unit prefix already carries a value that's equivalent to a power of 10, and it's all you do with it is you just tack it onto there. So in other words, for Q1, which is 7 microcoulombs, I would just write the 7, or whatever number I have here, times whatever power of 10 is associated with that unit prefix. So micro is 10 to the minus 6th, in this case coulombs, because it's a microcoulomb. So 10 to the minus 6 coulombs is a microcoulomb. So every time we see unit prefixes, this is what we're going to default to doing so we don't have to go through a lengthy conversion process, which will more likely make mistakes. All of this is over the distance, R31, which is 4 millimeters, 4 times, so again the same thing, unit prefix is milli, which is 10 to the minus 3. So we write the 4, and we carry through the power of 10 for the unit prefix, 10 to the minus 3. meters in this case. Do not forget to square it. If I got $1 for every single time that someone forgot to square this, I'd be rich by now. F31 equals, sometimes you even write the square and you just forget to put it in the calculator. It's so easy to miss it. So we have 4, 10 to the minus 3 squared, and that's in the bottom, multiplied by Coulomb's constant, multiplied by the charge of electron or proton, in this case it's electron, so times that charge, times 7, times 10 to the minus 6th. Okay. And I get that this force, magnitude-wise, is 6.29 times 10 to the minus 10th newtons. Okay, so we get that force there, but we're not done yet. We need to find the force F32 as well. So we're going to repeat this process real quick for F32. F32 equals K Q3 Q2 over R32 squared. Okay. So everything has to do with charges 3 and 2 now. We're going to ignore 1. K is 8.99, 10 to the 9th Newton meters squared per Coulomb squared. Charge 3 has a value of, that's the electron, so it's absolute value 1.6 times 10 to the minus 19th coulombs, times charge 2, which is negative 14 microcoulombs, so absolute value will be carry through the 14 times unit prefix is micro, so it's 10 to the minus 6th coulombs divided by the distance between charges 3 and 2, which is this distance, which we found to be 6, times unit prefix is milli, so 10 to the minus 3 meters. Don't forget to square it. Equals, calculate this real quick. 6 times 10 minus 3. Don't forget to square it. It's on the bottom. Multiply across. Coulomb's constant, charge of an electron, and 14. 10 to the minus 6th. So we find that this force F32, its magnitude, is 5.59 times 10 to the minus 10th newtons. Okay. So now, we have the magnitudes or the sizes of each of these two individual forces that act on the electron. Now, how do we find the total or the net force? So all that means is we just add them together. But since they're vectors, meaning they have direction on top of their magnitude, we also have to consider the directions, and that may affect the answer in terms of if we add them together or if we subtract them from each other. Now, we should say that the answers we got in terms of the directions, well, if positive x I'm going to define to the right, then these are both pointing to the left, which means they're both pointing in the negative x direction. So we should say that this, whatever we got, is in the minus x direction. And this is also in the minus x direction. Okay. So when we add these together, we're adding two things in the negative direction, so it should give us an answer which is something bigger in the negative direction. So when we do this, it's going to be negative this value, and we're going to add negative this value. So we should have that the net force, let's write it this way, sum of all forces acting on the electron, which is what we want to calculate, is just equal to F31 plus F32, which is going to be negative that value, 6.29. Now, I could write this whole number out, plug it in, write this whole number out, plug it in, but I will make the observation that because they share the same power of 10, I can factor that out and just write the 6.29 and the 5.59 and just deal with this later. So if I just factor that power of 10 out of both of them, it's minus 6.29 plus minus 5.59. Again, the minuses being from their directions. Put those together, and all of it is times 10 to the minus 10th newtons. Okay, so that's what I meant by pull it out, factor it out, and just worry about it later, because they both share the same power. Otherwise, just take that number and just put it together with that number. Equals. So we have 6.29 and 5.59. That collectively makes negative 11.88 times 10 to the minus 10th newtons. This is the correct answer, but if it bothers you that I'm not using a number between 1 and 10 here, you can move the decimal place over by one place to make this number smaller, which you then compensate by making this number bigger. So to make this number bigger, you go to minus 9 from minus 10. So this is the same as negative 1.19 if you round it, times 10 to the minus 9th newtons. And that is our net force acting on that charge in the middle. Now, this answer is negative, or at least can be negative, because you are now accounting for the directions with the minus signs. This is why we only calculate the magnitudes or the absolute values of these before, because it's very easy to handle the directions with just the signs here. So the minus sign in the answer means that it's technically in the negative x direction. That's what it means. Okay. And that makes sense because there's two forces to the left, so the overall force should be also to the left. So it makes sense.